All right, so quick little bit about me. So I'm Mike. Call me anything you want except for Michael or Mr. Swoboda. See here, I like baseball, basset hounds, bourbon, and The Bachelor, and I love Jesus, but I cuss a little. So there's that. All right, so let's get started with this nice, fun math stuff. So you've done linear and angular kinematics, which is essentially, your triangles and whatnot. Now, with the kinetics part, we're actually taking this into an area where we can have more of a practical application for this. So the big things that we're going to be looking at here are things like, say, your work, your power, your energy production. We'll look at torque. I'll probably review levers with you just because. Now, have any of you had physics before? Oh, that's awesome. Makes this super easy. So one of the things I'll provide you for your at least first exam, because it's really the only time you'll need it, is your kinematic and kinetic equation sheets. So you'll have all those equations available for you. The test is going to be all online. So what I'll do is I will post really a study guide for you and all that good stuff. And then I'll have the test open. I believe it should be, well, it's supposed to be, I think, next week, but I doubt we're going to end up doing that. And it seems like we're about a week-ish behind. And then I record all the Zoom sessions and I'll post them to the announcements page. Now, what I do is I upload them to YouTube, but I upload them in the wherever the unpublished setting. So the only way you'll be able to access it is with the link from the announcement section. Not that I don't want to make everything all public and whatnot, but just because of nice FERPA regulations, I'd rather not even kind of toe that line. So all your videos I'll post typically on Friday evening for the week, and then that'll be that. So I should ask, do you all have any questions for me here before we get started? All right, so let's get right into it then. So first off, Newton's laws, covered this yet? Okay, great. The ones that are most applicable to us are the first and third. So first law, objects in motion stay in motion. Third law, equal and opposite reactions. For a reaction, equal and opposite reaction. Third law of motion is the whole reason why you do not want super strength. Like being the Hulk would be the worst thing ever, because when you go to Hulk smash, that whatever you're breaking hits you back with the exact same force that you hit it. We'll talk about inertia a little bit later, but inertia is just your resistance to displacement. The higher your inertia is, the more stable you are. The lower your inertia is, the more mobile you are. This kind of comes into play when we look at like friction and doing our, say, like forces as they relate to like moving static or kinetic objects, that kind of thing. All right, force equals mass times acceleration. Pretty simple. Now, weight is a force, but we also have to be careful at how we look at this. In some of the kinetics homework with the other 335 class I'm teaching, you'll see problems like, say, for example, with like projectiles. And for some of the questions, it would be like your initial velocity is something like, I don't know, 50 feet per second, and you are going at an incline of, I don't know, 30 degrees from the horizontal. And then they're missing a whole bunch of this because they're mixing up their labels. So specifically, if you're trying to calculate the range of a projectile, the total flight time, or even the, like, say, max height, you have to take gravity into account. Well, what does gravity actually, or how much is gravity here?
It's a downward acceleration of 9.8 meters per second squared.
There we go. 9.8 meters per second squared. Do you already see the problem we're going to run into here? You have a velocity measured in feet per second, and then you have gravity measured in meters per second. So this is where I say you have to be careful with what your labels are to make sure you're not comparing two unequal measurements. So weight, you think of weight as your pounds, which is a force. What you want to convert weight or mass into, unless it's specifically asking for mass, is newtons. So what you would do, you take your weight in pounds, divide that by 2.2, which equals kilograms, multiply that by 9.8, and that'll equal your newtons. Mass doesn't take gravity into account. That's why mass is not a force. So if you're ever asked what a mass is, or what someone's mass is, that's always going to be in kgs, because that doesn't take gravity into account. It's essentially like your molecular weight kind of thing. Or if you want to be real slick about it, you take pounds and you multiply that by 4.45, and that'll give you newtons directly. All right, this here, the normal force. This is how Newton's third law actually applies to the regular world. So every time you take a step, you have a force exerting back up on you from the ground at that same amount that you are striking it with. This is also why, like, say, running on a treadmill is so harsh on your body, because you have very little room to dissipate the energy that you strike the ground with. So you are getting quite literally the same force coming right back up at you. Whereas if you're running on, like, say, a open surface, you have much more room to dissipate all that energy. So there's your little FF fun fact for the day. Now, the normal force is always perpendicular to the ground, up to 89 degrees. So it doesn't matter if you have the ground looking like any of these, your normal force is always going to be exactly perpendicular to that. Now, I'm not going to make you, like, say, calculate any of these ones here where you have to do an incline with the normal force, because then that gets you into more of, like, say, just the basic physics stuff of it. And, you know, since it's not a physics class, not really what I want to get too deep into. But just so you know, normal force is the force that exerts perpendicular to the ground. If we have a massless object, which I swear in, like, all examples, you have no friction and no mass, but what would your normal force be?
would be gravity.
Yeah. So if you have no external force acting on the ground, you just have gravity as your normal force. All right, friction here. And I really do this like great thing where I will explain like a full slide ahead of actually showing it to you. So just be kind of aware of that. All right, here are the two equations you need to know for friction, static friction and kinetic friction. Static friction means you are stopped. Kinetic friction means you are moving. Both of these are the same thing. This should be a mu, not a u. But your force is equal to just your coefficient of friction times your normal force. So it's pretty simple. Broadly speaking, you are going to have a lower coefficient of friction for kinetic friction than you will for static friction. And that's just because an object that's at rest is going to have a higher inertia than an object that's already moving. All right, so let's try these here. First off, how many of you are hitting a 5 kilogram golf ball? Because that's rather impressive if you are. So you got a 10 Newton force from a golf club acting on a ball weighing 5 kgs. What's the acceleration of the object? Okay, so what's the equation I'm going to use?
F equals ma.
Perfect. Force equals mass times acceleration. Gives me a force, gives me a mass. Pretty simple. 10 newtons times 5 kgs equals 50. I guess I would want.
I think you divide.
Do it.
I think you have to divide. 10 divided by 5.
Oh, shoot. I'm so sorry. Wow, yeah. So they give you the force. Wow. That's a little embarrassing there. Yeah, so there we go. So we got 10 newtons equals 5 kgs times your acceleration. So if I divide both of those by 5, my acceleration, then it becomes 2. Well, there's really no label here because we don't know what we're doing, but typically it's speaking as meters per second squared. You'll be able to tell the difference between an acceleration and a velocity because acceleration is meters per second squared. Velocity is only meters per second. I mean, all things considered, I'd say I'm doing pretty good so far. I mean, I've only got 2 screw ups in 15 minutes. I mean, if we go at this pace. All right. Coefficient of static friction is 0.1, kinetic friction 0.07. You got a 4-man bobsled team and a 400 Newton bobsled. How much force directed to the parallel of the horizontal is required to start the bobsled? So remember, our static friction is equal to our coefficient of friction times our normal force. Well, we're given our coefficient of friction here. And what is my normal force? All right, what I have here is I have 4 guys that weigh 300 newtons each. So that gives me 1,200 newtons. Then I also have a bobsled that weighs 400 newtons. Remember, newtons are a force. So I have a 1600 Newton force acting down on the ground, which means the normal force, which is opposite that, is going to be 1600. See how that works. This is why I say that we're not going to worry so much about like inclines, because if we had an incline here, that 1600 is going straight down, whereas the normal force goes perpendicular. So then you have to calculate how much of that force is actually exerted on the object. So I don't want to get too much into that. So anyways, 1600 newtons times 0.1. So 160 newtons is required to start that bobsled. Now, to keep it going, my coefficient of kinetic friction is 0.07, and I still have 1600 newtons of force. Does it kind of make sense why the kinetic coefficient of or the kinetic friction force is less than the static friction force? Once you're already moving, you need less force to keep moving, essentially. All right, questions on those two? All right, impulses. I'm not going to ask you to calculate these on your exam, but this will be on your homework. Yeah. So momentum is just essentially how much really motion you have. So when you're calculating momentum, all it really is just your mass times your velocity. Now, what's important with velocity is, remember, velocity is a vector, meaning it needs to have both a magnitude and a direction. So what would be my momentum if I ran a single lap around the track? Yeah, it means zero. If I have no displacement, I have no velocity. So kind of keep that in mind. So really just with momentum again, mass and velocity, that's pretty simple. Got to keep that in mind too. You can use weight, but you have to have everything equal. So make sure that you don't have like kgs on one end and pounds on another kind of thing. Impulse is just how much force over time you enact on something. So your impulse is just your force times time. So your change in momentum is also equal to an impulse. Don't worry so much about all the minutia with all the different equations with here. Just remember primarily this guy here, impulse equals force times time, and then momentum is just mass times velocity. All right, momentum of a 200 kg sprinter running across a finish line at 8.7 meters per second squared. So remember that momentum equals mass times velocity. How do we know that this is a velocity?
Meters per second.
Yeah. If it were an acceleration, it wouldn't work. But meters per second as a velocity. So all I'm doing, mass is 200 kgs, velocity 8.7 meters per second. So that gives my momentum there. It should be 16, 18, 10. 1740. Oh, never mind. I was thinking that was 3. Anyway, and the label for momentum is going to be kg meters per second. All right. Fastest recorded javelin throw was 35 meters a second. What's the impulse required to give a 10 kg javelin such momentum? So if we go back here, your momentum you can have as your change of momentum would be just force times time. If we have a kg or a javelin that is measured in kgs, it means we have a mass there. So I can get that from here. So if I go 35 meters per second, 10 kgs, that gives my momentum to be 350 kgms per second. Now, what I would then need to do is look at how to get impulse from that. So our momentum and impulse will be the same essentially there. So if my impulse equals force times time, which also equals my change in momentum, I know my momentum here is 350. So what I can say is 350 equals Ft.
Does impulse have a different unit?
No, it shouldn't. Now, here's kind of the tricky part is that we don't have time and we don't have the force, but we're given already our time essentially here, which is 1 second. So for our force here, it's going to have to then be 350 newtons of force there, since T is going to equal 1. All right. So momentum impulse they're good to know. I mean, if you went into like actual, like say research doing things like say sports performance or even like kind of biomechanical analyses, this would be stuff that's important to know. But in terms of what we really need for, say, our basic movement analyses, I'm not so concerned about impulse and momentum. What I do want you to focus more on is this here. So the work, power, energy bit. This is where it does a lot more applicable stuff for everyday use. So work, I don't like that they put the term distance here because really it's displacement. If you don't have displacement, you don't have work. So again, if I traveled all the way around a track, start and ending at the same point, I have no work because I have no displacement. So work simply is just force times displacement. You label work as either joules or Newton meters. Either one is perfectly fine. All right. Whenever you are, and I know I just say label it Newton meters and now we get foot pounds. When you label work, it has to be in all the same unit measurements. So it has to be all metric or all imperial. You can't intermix the two. So if we keep this all as pounds and feet, we can keep that as our torque, or not our torque, but as our work. So if you weigh 2 pounds and you lifted 6 feet from the floor, well, 2 times 6 is 12. That's pretty simple. Now, this here. All right, you are going to push a car 1,980 meters away. You're using a force of 2,000 newtons. So what's my work? And how do I know that this is actually a displacement?
Essentially, they were 1980 meters away from where they first started.
Yeah. I mean, you're going down Camelback Road, doesn't matter which direction you're going, but you are going down a direction. So you know that you are at a different place than where you started. So 1980 times 2,000. So that is 3.96 million joules. Now, the next thing we add to this is power. Power is just your work over time. And you measure power in watts. So if I had this many joules, how much time do you think it took to push this car? Don't all shout at once.
30 minutes, maybe.
Sure, why not? So all I have to do is divide my work over my time to get my power. Now, I can't leave this at 30 minutes. I mean, I can, but it's not going to come out to the exact correct measurement. What do I have to change this to?
Seconds.
Seconds, yes. So 30 minutes times 60 seconds per minute gives me 1,800 seconds. So I take my 3.9 million divided by 1,800, and that gives me a power of 2,200 watts. If you really want to have fun with this, you take that number, divide it by 748, and that gives you your horsepower. So they were moving at about 3 horses. That's not too shabby there. All right. Work so far. Is that good? I'm not gonna lie. So I teach the Monday, Wednesday ground class at 7 a.m. And we did this 2 weeks ago. And like midway through it, I was gonna tell you, like I feel like I'm boring myself by doing this. I mean, who really likes math at 7 a.m. and or 7 p.m. kind of thing? So I promise you, if you can get through this, like the class becomes so much more interesting once we actually get to do like movement with body parts and all that good stuff. All right, you bench press 275 newtons. You go 2 meters in 3 seconds. What's your power? Well, work equals my force times my displacement. So work equals 550 joules. Power equals work over time, which is 550 joules over 3 seconds. Which gives us 183 watts. Simple enough. The biggest problems I see students have with this stuff is mixing their units up and order of operations. I think we'd agree that, having to essentially multiply and divide by 2 and 3 is not the most difficult thing to do. But if you don't remember where to put your numbers, it makes it very difficult. And most problems we're going to have are ones that build on top of each other. So for example, with power, you're going to be asked to calculate work, then calculate power. Well, if you mess up work, you can't get power correct, right? All right, energy. 2 of these, potential and kinetic. To have potential energy, what do I need to have? Like what conditions must be met for potential energy to exist? You do have to have mass. That is one thing.
Gravity.
That is true. So assuming we're a person on Earth,
You have to be like fully static. Like can't be moving at all.
yeah, kind of. The big thing here is you got to be above ground, essentially. So if you are laying down on the ground, like flat ground, you have no potential energy because you have no height. Now you can argue if like you're walking on flat ground that you technically have potential energy because you fall over, you would crash land into the ground. So you're technically above the ground. But for all intents and purposes, you have to be above ground to have potential energy. For kinetic energy, you have to be moving. You can't have kinetic energy if you're not moving. You also can't have kinetic energy if you have no displacement. Although it's kind of hard to have no displacement and be moving at the same time. All of your energies are going to be measured in joules. Your work is measured in joules. Power is measured in watts. Yeah. So those are really the only two labels you need for those. All right. You had 205 joules of potential energy. How high is your shelf? If you have a box, it's 5 kgs. Well, potential energy just equals mgh. So 205 equals 5 kgs times 9.81 times x. Now, here's kind of, again, a bit of a tricky thing. You're not given what the unit is of height, but how do you know what that unit is? So how do you know, since h equals 4.2, what label would I use here?
Meters,
Why?
because you have kgs and pounds.
Yeah. I have gravity here. So again, remember gravity is meters per second squared. So you have meters. That's what that has to be. All right. Soccer player has a mass of 70 kgs. You have a velocity of 4.5 meters per second. What's your kinetic energy? Well, kinetic energy is 1/2 mv squared. So that equals 1/2 times 70 kgs times 4.5 meters per second squared. Now, what's the mnemonic you remember for your order of operations?
PEMDAS.
Do what?
Are you talking about like PEMDAS, like PEMDAS?
Oh, yeah, I didn't catch what you said there. So I always called it, please excuse my dear Aunt Sally. Is that what you all learned? How about, okay, what about the wrist bones? Did you ever or learn the mnemonic for that?
So long the pinky, here comes the thumb.
God, that sounds a lot dirtier now that I think about that. But you could use that, or some lovers try positions that they can't handle, is what I learned. Either way. But anyways, make sure you do this first. That's kind of roundabout way to say that. All right, any questions on these here? All right, so that is all your nice friction, work, power, all that good stuff. Now, let's get into the angular kinetics parts. That was all linear. Now we're into angular. All right, torque is the same thing as work, except it requires you to have an angular movement. So you may see, like, especially electric cars rated in, say, foot-pounds of torque rather than horsepower. Usually you don't rate like a car with horsepower that doesn't have like an internal combustion engine. So like electric cars, you typically would measure them in terms of, say, their torque they produce or their foot-pounds of torque. Well, you measure that at the tire level because the tires are spinning. You have that angular movement there. So that is what we're going to look at here. For torque to exist, you have to have a fulcrum or an axis point. So you have to have a rotational point. And you have to have a moment arm. So this here is your moment arm. This here is going to be your axis or your fulcrum. And torque is just how much force is applied to the moment arm and how much angular distance it travels. What is my theoretical maximum distance I can travel? Not 360, but that's a good guess. 180. Because anything past 180, you essentially subtract it, so you're getting closer to the starting point. Now, the easiest way to think about torque is how it applies to like a door. Virtually all doors have the handle opposite, or the essentially as far away from the hinge as you can. And you do that just so it's easier to open, close, move the door, right? None of you, I think, will open and try to move a door right next to the hinge. If we look at why that is, it will all tell you here. So let's say that my door is, I don't know, 1 meter. So that's from here to here. However, my distance from the fulcrum to part B is, let's go with 10 centimeters. If I apply a constant force, let's say, just for the sake of even numbers, let's say I have a 10 Newton force here and then here, you'll see how much my torque changes. So for A, torque equals force times my distance, which is equal to 10 newtons times 1 meter. So my torque is equal to 10 Newton meters or joules. For B, I have now a distance or a moment arm of 0.1 meters, and I still have that 10 Newton force. So that gives me a torque now of only 1 Newton meter. So what does this actually mean in real life for us? That torque is so much lower in point B. So what's essentially happening here is that if I were to push at this with the same force, but two different moment arm lengths, it's going to take me a lot more time to open that door at the shorter moment arm length because I have such less torque production. If I wanted to equal out torque, so if I wanted A to equal B, so net torque, you would have your 0.1 meters times what my force would be minus 10 Newton meters. So 10 equals 0.1 F divided by 0.1 divided by 0.1, and then force would equal 100 newtons. So you see how much more force I would have to exert to equal torque based on a longer moment arm. Is that kind of making sense, or am I just kind of rambling? All right, so we just talked about that. Now, if you were to apply force at the axis, or if you were to go apply force parallel to the axis, what's my torque going to be?
0.
Yeah, big old goose egg. In both of these cases here, what's not happening?
Is it displacement?
Yeah, there's no movement there. If I push at the axis, that means my moment arm is equal to 0. If I push parallel to the axis, it means that I have no net force being applied to produce torque, because the only way you have torque is if you have angular force. So you need to be moving perpendicular to the axis, not parallel to it. If you think about it, if you push a door at its hinge, it's not going to move at all. If I push a door on the long side of it, it's also not going to move. This is the trickiest part with torque, and that's when you don't have your force being applied directly perpendicular to the moment arm. This is going to go back into your geometry or trigonometry bit here. So when you are calculating torque, it's always going to be the length of that moment arm times your force. Oops. When your moment arm, or I'm sorry, when your force production is not perfectly perpendicular, your moment arm length changes based on the angle of the force production. So your force will stay the same regardless of which direction you go. Your moment arm is going to be the thing that changes. Are you with me there? Okay, so you can see here how you turn this into a right triangle, and then it becomes very easy to do. What you'll know is you'll know how long your moment arm is, right? So let's say that this moment arm is 5 meters. What part of the triangle is this?
Hypotenuse.
Yes, this is your hypotenuse. You know this is going to be your 90-degree angle. And the force line is going to be typically the angle you're given. So knowing those, what equation am I going to have to use to figure out what the actual length of my moment arm is?
Opposite over.
Yeah, you're going to do your sine of theta is equal to your opposite over hypotenuse. So keep that in mind. All right. For this here, you have a 7 Newton force, 3 meters for your moment arm, 30 degrees off axis. Now, where this is tricky is having to accurately draw a line here. If your moment arm, or your calculated moment arm, is greater than the actual moment arm, you are wrong. Because why?
So hypotenuse is the longest.
Exactly. Alicia, I think you're muted there. Are you trying to say something? Or are you just talking to other people? That moment when you realize that you're not paying attention and the professor calls on you. All right, so all I have to do here is I'm taking sine of 30 equals my opposite over my hypotenuse. So 0.5 equals x over 3 multiplied by 3. And I get x to equal 1.5 meters. Now, what does that 1.5 meters tell me?
How long that side is?
This is how long our calculated moment arm is. So because our force is off-centered, our calculated moment arm gives us what the actual moment arm length would be if we applied this force directly perpendicular to the axis. So now we go and do our torque, which is just 7 newtons times 1.5 meters, which equals 10.5 Newton meters. 4 joules. If you can do this, that's the hardest thing you'll have to do. Surprisingly, I saw a lot this year so far of students who have been multiplying by the numerator instead of the denominator. So I've seen this quite a bit. And they would cancel this out and call this then 3. So make sure I know it's hopefully pretty basic, but make sure you're multiplying when you are canceling out. You're multiplying by the denominator and not the numerator. All right, we're going to get more into this here next week when we actually do the well, next week. This is only Wednesday, so on Friday we're going to get more into this when we start talking about like muscles and whatnot with it. This here is real simple. If I have that perpendicular force, 7 newtons times 3 meters, 21 newton meters, that's my torque. Pretty simple. Okay, static torque. We'll finish up with this and then kind of call it a day here. All right, when I have static torque, what I am measuring here is how to stay stationary. So you don't want to have any movement when you are static. Makes sense? What you'll use is the term sigma T, which is your net torque. So net torque is going to equal torque 1 minus torque 2. And it doesn't matter which side you go, because since these have to equal 0, it doesn't matter if you call this side 1 and this side 2, or if you call this side 2 and side 1. Does not matter. As opposed to if I was talking about, say, velocity, you would start with your initial velocity and you would start with your end velocity and you'd subtract your initial velocity from it. You can't do it the opposite way, so you can't start with your initial velocity subtracting by the end velocity. Otherwise, you have a negative number. But because these two sides equal 0, doesn't matter. So keep this in mind that your net torque is going to equal 0. Okay? So for this, the weight of the head forward looking down is 10 pounds. Distance from the center is 4 inches. So you got 4 inches, you got 10 pounds. Neck extensor muscles are 3 inches posterior, and how much is the force they require to keep this static? All right, what's the first thing I need to do here?
Convert your units over.
Yeah. So I want to convert inches to meters. So there's 2.54 inches in a centimeter. 100 centimeters in a meter. So 3 inches equals 0.076 meters. And then four inches equals 0.1 meters. I'm also not worried about sig figs either. I'm doing this based on my own convenience here. So yes, while I realize that there are 3 sig figs I'm using here and only 1 there, I am not too particularly concerned with that. And then pounds, I should convert that to newtons. So if I take 10 pounds divided by 2.2 and then multiply that by gravity, that gives me the newtons I have. So 10 pounds equals 44.6 newtons. All right, we're good so far. So my net equation here is 0 equals 0.076 meters times x minus 44.6 newtons times 0.1 meters. So 0 equals all right, so see how I got this set up here. So then add 4.46 to each side. Divide it by 0.076. Equals that. And what is that?
Force going up.
And what do I label that?
That'd be newtons.
Yes. So that is newtons. So net force I need, 58.7 newtons. Easy way to check that is just plugging this back in. So does 0.076 times 58.7 equal 44.6 times 0.1? And should come out to that 4.46 that we had. So that is net torque, or I should say static torque. Again, when you're looking at static torque, your total system is neutral. You're not moving, so it has to equal 0. If you were moving, then your net torque would equal something else. All right. I know it's kind of a hodgepodge of a first class, but I do appreciate you all getting through this with me here. What kind of questions do you all have so far? All right, well, if you all have any more questions, you guys are all good to go. Thank you for getting through all this with me. And then I will see you all back here on Friday.
Thank you.
Thank you.